Welcome back to Basic Electronics. In this class, we will start looking at diode rectifiers. To start with, we will discuss the general functionality of rectifiers and the meaning of the terms half wave and full wave rectifiers. We will then look at how addition of a capacitor filter changes the output waveforms. So let us begin. We will now look at diode circuits for the purpose of rectification. A rectifier is used to convert an AC voltage to a DC voltage, which is typically in the range 5 to 20 volts. The AC voltage is generally the AC mains voltage, 230 volts RMS. And a common example is a mobile phone charger. Now in doing this, we have two possible approaches. One, we start with the AC mains voltage, step it down to a lower AC voltage and then convert it to DC. So that is one approach. The second approach is we start with the AC mains and directly convert it to a DC voltage. So this DC voltage would be a large DC voltage, and then convert that large DC voltage to a smaller DC voltage using a DC to DC converter. In this course, we will look at this first approach as illustrated in this schematic diagram here. We have the AC mains, and that voltage is stepped down with this step down transformer. After that, we have the rectifier without filter, and we will very soon see what is the meaning of this filter here. And finally, we have the load, and here we have shown the load as a simple resistor. In real life, it could be something else. And this voltage, the output voltage, is taken across the load. And our intention is to have VO as a DC voltage. Okay, let us now look at the waveforms. Here are the waveforms for a half wave rectifier without filter. This blue curve is the input voltage, the step down input voltage as it appears over here, and the pink one is the output voltage VO. So when VI is positive in this first half cycle, VO is equal to VI, and when VI is negative, VO is equal to 0. And it should be clear why this circuit is called a half wave rectifier. In half of the period, the first half here, VO is non-zero, and in the second half, VO is 0. So that is why half wave rectifier. Here are the waveforms for a full wave rectifier without a filter. The blue waveform is the input voltage again, as it appears here, and the pink waveform is the output voltage. And the difference between these two cases is obvious. In the full wave rectifier case, if VI is positive, then VO is equal to VI, and that part is similar to the half wave rectifier case. But here, when VI is negative, the output voltage is not 0, but it is minus VI. That means it is positive. So here the output voltage is non-zero and positive in both these half cycles, and that is why it is called a full wave rectifier. Note that this waveform is not what we are looking for. We are looking for a constant output voltage. So therefore, we are looking for a rectifier with filter. Nevertheless, it's useful to look at these circuits, rectifier without filter, because that will make us understand this one better. Let us look at the waveforms in this case. That's the input, that's the output of half wave rectifier without filter, and that is the output, the dark red curve of a half wave rectifier with filter. So it's almost constant except for some small variation which we call as the ripple voltage, and that is the situation for a full wave rectifier with filter. So that is the input, that is the output if we did not have a filter, and that is the output of a rectifier with filter. Again, there is a small ripple voltage that we can see. Now typically a voltage regulator would be used after this stage because we don't want this ripple voltage to be riding on our DC output. So we would have AC mains, then step down transformer, then rectifier with filter, then a voltage regulator, and after that the load. That is if we go for the first approach. And similarly we can also have the second approach implemented involving a voltage regulator. Here is a half wave rectifier without a filter. Now this AC source could be the AC mains, or it could be a step down version of the AC mains if we use a step down transformer. Now the diode D conducts only if Vi is greater than V on, and in that case Vo is Vi minus the turn on voltage of the diode, that is Vi minus V on. That's a straight line with a slope equal to 1, that is shown over there. And if Vi is less than V on, then D does not conduct, therefore there is no voltage drop over there, output voltage is 0. Here is the time domain picture. The blue waveform is the input waveform and the pink one is the output voltage waveform. D is on in this interval and it is off in this interval. And when D is on, these two are not exactly coinciding, and that is because of this small V on voltage drop across the diode. Here is a full wave rectifier without a filter, and it is also called a bridge rectifier because we have this diode bridge here. The AC source Vs is connected between nodes A and B, and the load, the resistor here R, is connected between nodes P and Q. Now let us look at the current path when Vs is positive and when Vs is negative. When Vs is positive, node A is at a higher potential than node B, and the current flows from the source through D1, through R, then through D2 and then back. When Vs is negative, node B is at a higher potential than node A, and then the current flows from the source through D3, through R, through D4 and then back. Now the important thing to notice is in both these cases, that is with Vs positive and with Vs negative, the direction of the current through R is like that, the same in both cases, and therefore Vo is always positive, and that is why this is a full wave rectifier. Let us redraw this circuit in a more friendly format, which is easier to look at, as shown over here, and let us make sure that these two circuits are actually the same. The source is between nodes A and B here, and it's also between nodes A and P here. The load is between P and Q, and that is true here as well. D1 is between A and P, D2 between Q and B, D3 between B and P, between B and P here, and D4 is between Q and A, and the same thing here between Q and A. So these two circuits are identical, and let us now use this circuit for our further analysis. Let us consider Vs to be positive. Then node A is at a higher potential than node B, and the conduction takes place through D1, then the load resistor, and then through D2. Now if there is no voltage drop across D1, so let's say V on is 0 for D1 and also for D2, then node P is at the same potential as node A, and node Q is at the same potential as node B. So in other words, the output voltage VO is then equal to the input voltage Vs. In reality, of course, there would be some voltage drops across D1 and D2, V on equal to say 0.7, and then the output voltage would differ slightly from the input voltage. Let us consider the other case now, Vs negative. Now node B is at a higher voltage compared to node A, and the conduction path is through D3, then through the load resistor, and through D4. And in both of these cases, note that the current is downward here as well as here, and therefore VO is always positive, and that's why it's a rectifier. Once again, taking the simple case where the on voltage of the diodes is 0, this node P is now at the same potential as node B, and node Q is at the same potential as node A. In other words, VO is now equal to minus Vs, and in reality, of course, there will be a slight difference because of the V on of the diodes. Let us look at the waveforms now. The blue curve is the input voltage Vs, and that goes from plus Vm to minus Vm. The dashed curve is minus Vs. In the first half cycle, when Vs is positive, we have seen that D1 and D2 conduct, and in that case VO is nearly equal to Vs, and that is what we observe over here. And the difference between these two is the V on drops across the diodes. In this half cycle, Vs is negative and minus Vs is positive. In this case, D3 and D4 conduct, and as we have seen, VO and minus Vs are nearly equal, and that is what we see over here. That is VO, that is minus Vs, and they are nearly equal. The difference, of course, is because of the V on drops across D3 and D4. Let us now look at the half wave rectifier with a capacitor filter, and it is similar to the half wave rectifier circuit we have seen before, except for the capacitor. In the half wave rectifier, we had the diode and the load resistor, and now we have this capacitor added in parallel with the load resistor. Now this circuit is very similar to the peak detector circuit that we saw earlier, in which we had the diode and the capacitor, but not this load resistor. And as a result, what happened is this output voltage tracked the peak of the input voltage. Now this circuit is not quite the same, but it's very similar. The difference is that in this case we have a load resistor which is going to draw a current, and therefore that current will provide a discharge path for the capacitor. In the case of the peak detector, this was not there, and therefore there was no path for the capacitor to discharge because the diode cannot conduct current in the reverse direction. Perhaps the easiest way of looking at the off-wave rectifier circuit with capacitor filter is to imagine that this resistance is infinite, and if that is the case, then the circuit is the same as the peak detector circuit. And then what's going to happen? The output voltage is then going to be equal to the peak of the input voltage. And what is the peak of Vs? Vs varies from minus Vm to plus Vm. So the output voltage is going to be plus Vm, and that will be held constant. Of course, there will be this V on voltage drop across the diode, but if V on is negligible compared to other voltages, then we can say that the output voltage is constant. And now let us look at what happens in the presence of a finite load resistor, that is when the load resistor starts drawing a current. These are the waveforms. This is the input voltage Vs, that is the output voltage Vo, that is the voltage across the diode, that is the diode current, and that is the capacitor current. First, we note that the diode conducts only in a very short interval compared to the period of the waveform, and that corresponds to this part of Vo. And when the diode is not conducting, we have only this circuit. By this time, the capacitor has already charged to Vm, and now the diode has stopped conducting. So what happens is the capacitor starts discharging through this resistor, and that is why we see a drop in Vo. At this point, the input voltage rises again above the output voltage, that is the P end of the diode is now higher than the N end of the diode, and the capacitor gets charged again, and this process is instantaneous because the time constant for this charging is very small. Why is it small? Let's look at the circuit from the capacitor. What we see is this resistance and the diode resistance in parallel, and that is of course nearly equal to the R on of the diode, which is very tiny. Because the resistance seen by the capacitor is very small, the time constant for the charging process is very small, and as a result the output voltage follows the input voltage instantaneously, and that is what we see over here, and that goes on up to this point, and now the input voltage starts decreasing. So the voltage at the P end of the diode is now going down. This voltage has not really changed, and therefore the diode stops conducting. And now this part is isolated from the rest of the circuit. So we have this RC circuit. The capacitor now discharges through the resistor, and that is what we see over here once again, and this process goes on, and because of this we see a small variation in the output voltage. It is not quite Vm, it's close, but there is a small voltage drop in Vo. So because of the load current IR, this current, there is a drop in the output voltage, and that drop is called the ripple, and it's denoted by VR, R standing for ripple voltage. Let's also look at the currents. As we have already remarked earlier, the diode current is non-zero only in this small interval when the capacitor is charging. Then the diode turns off, so zero current, and then again the charging interval comes, and the diode current becomes non-zero. Now it turns out that the diode current here is very large compared to the average IR. And do we see that average IR anywhere in this figure? That is right here. This figure shows the capacitor current, and in this interval the diode is not conducting, and therefore IC and IR are the same, of course with the negative sign. So IC then is minus IR, and you can see that this is our 0 here, and the IC value, which is the same as IR in magnitude, is very small as compared to the diode current here. These are drawn, of course, on the same scale, although the scale is not shown. So that's another very important observation to make, that is, the peak diode current is much larger than the average load current. The peak diode current turns out to be much larger than the average load current. What is the meaning of this? The peak diode current means the maximum instantaneous current that flows through the diode, and that turns out to be much larger than the average value of this resistor current, that is IR. Now, why is this peak diode current important? That is because when diodes are fabricated, each diode has a certain maximum current limit. For example, some diode may be able to conduct only up to 10 milliamps, some other diode might be able to conduct up to 10 amperes, and so on. So when we design a circuit like this, we must know beforehand what is the maximum current that is going to flow through this diode, and therefore we can choose a diode which has a maximum current rating higher than that particular value. Next, let us look at VD, the diode voltage. What is that given by? By KVL, we can say that Vs must be equal to Vd plus Vo. So therefore Vd is Vs minus Vo, as given by this equation here. What about Vs of t? That is Vm sin omega t or Vm cos omega t, depending on where we take the origin. What about Vo of t? Vo of t is nearly constant, provided this ripple voltage is small, and that is indeed the case in practice. So therefore we can say that Vo is nearly equal to Vm. We are interested in finding the maximum magnitude of Vd of t. Now we know that Vs of t varies between minus Vm and plus Vm. When Vs is plus Vm, Vd is 0, Vm minus Vm, and when Vs is minus Vm, Vd is equal to minus Vm minus Vm, that is minus 2 Vm. So therefore we expect Vd to vary between minus 2 Vm and 0, and that is indeed observed in this plot here. This is our Vd. The maximum value is 0 volts, and that happens when the diode conducts, and the minimum value is minus 2 Vm. And when Vd is minus 2 Vm, the diode is obviously under reverse bias. Now we might ask this question, why is this Vd important? Why do we worry about it? And the answer has to do with something called the peak inverse voltage or PIV rating of the diode. This rating specifies the maximum reverse bias that the diode can withstand. As an example, let us say Vm is 10 volts. In that case, the maximum reverse bias that the diode will come across is 2 Vm at that point, and that would be 2 times 10 or 20 volts, and therefore we must pick a diode with a PIV rating more than 20 volts. Finally, let us take a look at the results when V on is not 0 but 0.7 volts. and the plots are slightly different. Here we have plotted VO, the yellow line there, and VD when V on is 0.7 volts. Now as we see, the maximum value of VO is not Vm anymore, but it is Vm minus 0.7, and that is because we have this diode voltage drop here. So this node doesn't really reach Vm, but Vm minus 0.7. Apart from that, we don't really see a big difference between the earlier VO and this VO. The ripple voltage also remains approximately the same, and also the diode voltage is nearly the same as before. We have not shown ID and IC when V on is 0.7 volts, but this circuit file is available, and you can run the simulation and verify that the results are not really too different.
To summarize, we have looked at the meaning of the terms half wave and full wave rectification. We have seen an implementation of a half wave rectifier with and without a filter, and observed the associated waveforms. We will continue this discussion in the next class. Until then, goodbye.